Okay, let's get started. So, welcome you all to the live session 4 on the post manufacturing process technology first and second. So, in this live session, we will be solving some of the practice assignment problems based on the lectures of the week 5. So, let's get started. This is the first problem. Please try to solve it by yourself first. Then we will discuss it together. So you can give your response in the chat box. Please read the problem and you can give your response in the chat box. After that, we will discuss it together. I am waiting for a response in the chat box. If you have any difficulty to understand the question, you can ask me. Okay, okay, let me try to help you out. So, first, let's see what has been asked in the question. So, it is it has been asked that what will be. Okay, okay, Silam, I have got your response. Okay, let's start discussing together. So, what will be the surface obtained when generatrix and directrix are circular and straight line respectively? Yes. So, question is what will be the surface obtained when generatrix and directrix are circular and straight line respectively in tracing process? So, before that, let us try to first understand some basics like in the machining process. So we know in machining process our main objective is to remove the material, remove the unwanted material from the workpiece. So basically we have some workpiece like this and we want to remove some material from it using a tool. So this is workpiece and this is tool. And what we do, we try to give some sort of motion either to the workpiece or to the tool, either both. And because of this relative motion, we are going to create some desired surface on the workpiece. So there are basically two motions are involved. Either our tool can move or workpiece can move or both can move. So based on this, there are two types of motion. First one is the primary motion. Primary motion. So uh, the definition of primary motion is relative motion between the tool and work which is responsible for the cutting action. responsible for cutting action. And same time, because of this motion, most of energy is gets consumed. So the primary motion is responsible for the cutting, and it absorbs most of the power to perform the machining action. Perform machining action. So this is the primary motion. And similarly, we have secondary motion. Secondary motion. And it is defined as like it is responsible for gradually feeding the uncut portion and may proceed in steps. Proceed in steps or sometimes continuously also. And it absorbs only a minor fraction of the total power. So only a fraction of power it absorbs because of the secondary motion. So required for the machining. So these there are two types of motion. One is the primary, one is secondary. And primary consumes major portion of the and total power, and secondary consumes lesser portion. And because of these two motion, what what we what we are going to get, one is the generatrix. What is generatrix? So it is associated with the primary motion. The line generated by the primary motion or cutting motion. Similarly, the another term which has been asked in the question, that is directrix. What is this? This is the line representing the secondary motion or the feed motion. Or feed motion. Okay, so uh, these are some of the fundamental things which is required, or which is involved because of the motion of the tool and workpiece. And we are going to create some sort of desired surface with the help of primary motion, secondary motion, or generatrix and directrix. So let's take some few example. Okay, but I need to add some slide. Okay, now let's take some example which will suppose we want to create a flat surface. So how we can create? There are many ways to create a flat surface. Suppose if we take a line like this, okay, and we keep on stacking these lines very closer. Finally, what we will get? We will get some flat surface. So here the primary motion was this line. So that will called generatrix or G. But this generatrix is moving along another line. So this is called directrix. Similarly, suppose how if you want to create flat surface, there is another possibility. Suppose we are having a circle like this, small circle, then bigger circle like this. If we keep on increasing the diameter of circle, then again we will get some sort of flat surface. So what is generatrix? So these circular motions are generatrix. But if you see we are going outward or increasing the diameter, that is called directrix. So here by the combining two types of motion or generatrix or directrix, we are able to create a flat surface. Similarly, if we go and see what has been asked in the question, here it has been asked the generatrix is circular and directrix is straight line. Let's try to make it. So generatrix is circular like this and directrix is straight line. What will happen if we try to trace if you try to trace the directrix with the help of generatrix? What will happen? So what will, if we combine with these two motion, we will get something like this. So generatrix is moving along directrix, and finally what we are getting, if they are very close, what we will get a cylindrical shape. So the correct answer for the first question is D, cylindrical. Similarly, many ways you can see any type of machining operations. Always you will find two types of motion, primary and secondary, and you can easily find what is generatrix and directrix. Okay, so if any of you have any doubt in this question, please ask me, or we shall move to the next question. Okay, it seems there is no doubt. So let's move to the second problem. Thank you, Hamid. Please read the second problem and try to try to give the answer in the chat box. After that, we will discuss it together. Okay, I have got response from Sriram, I'm waiting for others. Okay, correct. Yeah, all of you are correct. So let's quickly discuss this problem. So which of the following is not true for the shaping process? So why shaping process is used? You can you have seen in your workshop this kind of machine. So this is nothing but it is a shaper machine. So the objective of this machine is to create flat surfaces. So what happens? Suppose if we have some workpiece like this, which is kept over the table or here something like this. Now the top surface which is here, is it is not flat or it has some roughness or aspective, but we want to make it flat. So what happens? There is on a tool head there is a provision of there is a tool. So tool is attached to the tool head, and now what happens? This workpiece is fixed, and what happens? This tool reciprocates front and back, and same time we are giving a feed motion to the tool. So like in this direction. So after each pass, we are giving some feed to the tool so that our whole workpiece, so that we could able to get flat surface. So this is the tool. This is a tool, and here what tool is doing? Tool is reciprocating. Tool is tool is reciprocating, and we are giving some feed to the workpiece. So it is not fixed. It is we are giving some feed motion to the workpiece. So let's say in that direction. So this is how a shaper machine creates the flat surface. So let's start looking at the options. So cutting tool is provided reciprocating motion. Yes, it is correct. Workpiece is fed parallel to the cutting motion. No, basically workpiece is fed perpendicular to the cutting motion. We can see here if you want to show it by axis like this and something like this. So this is the axis of the tool, and our tool is reciprocating. Suppose it is x, y, and z. So our tool is reciprocating along x direction, and our workpiece we are giving it some feed motion along y direction. So x and y are perpendicular, not parallel. That's why this option is correct. And see, it is called intermittent cutting. Yes, it is called intermittent cutting because uh, for what we are doing after one pass, we are again giving a little feed motion, and then our tool is cutting the uh, then again we are giving cutting motion to the tool. So step by step we are creating a flat surface. That's why it is called intermittent cutting. And it is used for creating a plane surface for a very long workpiece. So for shaping, this statement is not correct basically, because in shaper machine is used for creating flat surface for a smaller workpiece, not the longer workpiece. So basically, process, if even if we want to create uh, a flat surface for longer workpiece, the process will be almost same, but the machine or the process that which is particularly called, that is called planing. So why we cannot create longer surface uh, in the planer work, in the shaping machine which is in the workshop? Because we have very limited flexibility of, or we have big, this tool head, this is the tool head, it can move only a limited distance. But suppose if we are having very long workpiece like this, uh, we can not able to create flat surface because our tool can move only this much length. In that case, what we do, we provide we provide feed motion to the tool and cutting motion to the workpiece, so which has been shown here. Okay, so this process is called planing process. Here if you see, here the cutting motion is given to the tool and feed motion is given to workpiece, but here opposite is happening. Here cutting motion is given to the workpiece, feed motion to the tool. So although the process is almost similar, but the only here the exchange of the motion, like feed and cutting. So if we go technically, this D is not correct answer, but uh, more or less the process is same. So although we can create plane surface, but not very long surface. So the correct answer, which is not true. So if we go strictly, then both statements B and D both are not correct, but more accurate one will be this one, which is absolutely not correct. Workpiece is fed perpendicular direction, not in the parallel direction. So although statement D is also not correct, because for the longer surface, for very long workpiece, the planing should happen, or the process is called planing. Okay, but the more accurate answer is, if you have to choose one, then B is the more accurate answer. So is it clear, or any of you have doubt? Okay, it seems there is no doubt, but still, if any of you have doubt, you can ask me later also. So let's quickly move to the next problem. Please read the problem and you can give your response in the chat box. Okay, I am waiting for others. Okay, I have got a quite mixed response. Okay, let's try to discuss, and then probably after that it will become clear. Okay, which of the following is correct for up milling? So let's quickly see the diagram of the up milling. So in in the milling process, what we are doing, what we used to do, we have a milling tool and we have a workpiece, and with the help of milling tool, again we are trying to create a flat surface. So this is our milling cutter. So this is the workpiece. Okay, so if you see the milling cutter, so we have two options. Either it will rotate clockwise or it will rotate anti-clockwise. Similarly, workpiece also have two options. Either it can go left or right, or it can go left. So now let's try to see the situation of up milling. So for up milling, suppose our milling cutter is moving counterclockwise direction, which I have shown in green, and same time we have to also suppose our workpiece is going left direction. So if we have this kind of configuration, then it is called up milling. How I will also explain why it is called up milling. Basically, if you see the motion at this point here, if you see the tangential motion of the cutter, then you will see it is going rightwards, whereas the motion which is giving to the workpiece, it is leftward. Here we can see both direction of the cutting motion and the direction given feed motion is totally 180-degree opposite, because of which what happens, let's try to see the options. So first one is the upward force tends to lift the workpiece. So now cutter is moving like this, and it comes in the contact to the workpiece, let's say from here, and from here it keeps on rotating and it goes like that. So what it is doing, since the direction is like that here, that the tooth is moving from here to here like this, and because of this, if you see at any point, there are two components of the velocity. Suppose this is the velocity vector of the cutting motion, then it can be resolved into the two components. So one will be opposite to the direction of feed, or we can see v vf, and another one is towards upwards, or we can say it vz. So because of this vz component of the velocity, a upward force will come on the workpiece. So it is correct. Another one is easier chip disposal. So, so here, if we, what is the meaning of easier chip disposal? So what is happening here? Here our we have a cutting tool, and our workpiece is moving. So what is happening here? Our chips are getting moved towards upwards, like here. Whatever chips are getting formed, they are they have been thrown backside, and what will happen? They will again fall back on the workpiece. Okay, so our workpiece also moving towards the left direction, and chip is falling on the same face. Then it is very difficult to remove the chips. Suppose there are the few chips which are very closer to the cutting tooth. How we are going to remove? It is not possible to remove. Therefore, removal of chip is difficult for, for the up milling process. Therefore, it is not easy to dispose. That's why this option is wrong. And C is the cutting and feed direction are the same. No, we already have seen that for up milling configuration, the direction of feed motion and cutting motion should be opposite. So this is also wrong. D is the less power required. So what is happening here? For simplicity, I am taking circular cutting tool, which is do something like this, and we have a workpiece like this. So our workpiece is moving opposite and to the and our cutting tool is moving in counterclock direction. Since both are having opposite direction of motion, like here this is the cutting velocity VC and here is the VF. Since both are in opposite direction, then the force or the reaction force which is required, and as well as the friction force, that will also be higher, because relative motion will be between the workpiece and the tool will be higher. And because of this higher speed of relative motion, the forces applied as well as the friction heat generated because of the friction, that will also be the higher. So not less power, where less power is required, it is not correct. Higher power is required in the case of upmilling configuration. Therefore, the correct option for this problem is first one, the A. So, uh, any of you have doubt regarding this question? Why the A is the correct answer? Please feel free if you have any doubts. Okay, it seems it is clear to everyone. So let's move to the next problem. So it is also similar to the third problem. Please read it and try to give your response in the chat box. Yeah, I got response from Srinivas. I'm waiting for others. Okay. Okay, so let's start discussing this problem. So here this problem is all about down milling. So in earlier case we have seen the case of the up milling. There we saw that the cutting motion and the feed motion that should be in opposite direction. So in the case of down milling, what happens? Let's try to see. So here we have a cutting tool which is rotating in clockwise direction, and workpiece is moving towards left. Okay, so again similarly, if we try to see what is happening here, here if we see the tangential component of the velocity of the milling cutter, that is also towards the left, or we can say here the cutting velocity is parallel to the feed feed velocity. So this is the difference which which uh, this is the difference between the down milling and the up milling. But because of this condition, cutting velocity is parallel to the feed velocity, what are things are going to happen? So we can see here the tooth is going to engage at this point, and finally it is leaving somewhere here. So if you recall the earlier case, here what was happening, our tooth was engaging at this point and it was leaving somewhere here. Okay, so when tooth was engaging to the workpiece at that point, the thickness of chip is 0, but when it is leaving here, the thickness is the maximum. But here opposite is happening. Here the tooth is where tooth is engaging, there we are getting the maximum chip thickness, whereas where the tooth is leaving, here we are getting the minimum chip thickness or 0 chip thickness. And same time, the cutting speed and then feed velocity both are in the same direction. So because of that, what will happen, there will be less relative motion or relative velocity between the workpiece and the tool, and because of which less friction will occur, and the cutting power requirement will also be less. If cutting forces are low, then cutting power will also be low, and same time our tool will damage less. If tool will damage less, that means tool wear is slower, not the faster. So the first one is wrong. In this case, tool wear should be slow because cutting forces are less. And second option is width of chip start at maximum and then decreases. Yes, it is correct. It is correct. We already explained why it is happening. We can see that the tooth, where tooth is engaging, at that point we are getting the maximum chip thickness, or chip width, not the chip thickness. And surface finish obtained is not good. So if you have gone through the lecture, it has been explained that the surface roughness the surface roughness is lesser in the case of down milling because the surface deformation is less. In earlier case, in the in the upmilling process, the deformation was more because the relative velocity was more, but here the relative velocity is high, and the direction of feed as well as the direction of the cutting velocity, they are similar, and the relative velocity between the tooth and the workpiece, that is also smaller, so the severity of deformation is the less. Therefore here we are getting good surface finish rather than poor. So this is wrong option. And as already we told that in this case less force is required for the cutting, therefore cutting power will also be less, not more. So this is also wrong. Therefore the correct answer for this problem is B. So any of you have any doubt in this problem? Is it clear to everyone, or still there is some doubt? Okay, it seems there is no doubt, so we will move to the next problem. Please read the question, and first of all you can uh, try to find out how to approach this problem, and then you can try to solve it and give your response in the chat box. Please let me know if you are not able to understand the problem. If you are finding difficulty to understand the question, please let me know. And if you have understood, then you can tell me means how you are going to solve it. Any of you have got any part of this answer? Because two things have been asked: what is the shear plane angle and what is the shear strain? So any of you have got any part, you can give in, you can write in the chat box. And if you are finding any difficulty, so I will discuss it together. Okay, let me try to help you out. So so what is been asked in the question In orthogonal cutting, in orthogonal cutting operation, the tool has a rake angle of 15 degree. The chip thickness before cut is 0.3 mm, and the cut yields deformed chip thickness of 0.65 mm. So we have to find out shear plane angle and shear strain. So let's quickly try to understand what is the rake angle, or what is the uncut chip thickness, what is the deformed chip thickness. So this schematic, from this schematic, it is, we try to understand what is happening. So before that, first thing, can any of you confirm that do you understand the orthogonal cutting? Means what is the difference between orthogonal cutting or and uh, incline cutting? Okay, so basically it is simple only. So it has been defined by the uh, cutting edge of the tool and the cutting motion. So if cutting edge of the tool, suppose we have a cutting tool like this. Okay, so we have the cutting tool like this, and we have workpiece like this. So what will be happening here? Chip formation is happening. So what is happening? The cutting motion is in this direction. Okay, so if the tool edge or is perpendicular to this cutting velocity, in that case what we call it orthogonal cutting. But if our cutting edge is not perpendicular, it makes some angle like this. So if it is not 90 degree, if it makes any other angle apart from 90 degree, then we will call it inclined cutting or non orthogonal cutting. So after that, let's start observing this schematic diagram. So it is a case of orthogonal cutting. So what is there? This is the tool. Okay, Srinivas has given response. Yes, it is correct. So here we have tool, and this this face, this this surface is called the rack face. Okay, and how much angle it makes, the rake angle makes with the perpendicular, this perpendicular. What is this perpendicular? This perpendicular is nothing. This perpendicular is the perpendicular to the cutting velocity. So everything in the machining operation is taken with respect to the cutting velocity. So this perpendicular is the perpendicular to the cutting velocity, and how much angle it makes with the rack face, that is called the rake angle. Here it has been denoted by alpha. So that is the rake angle. And what is the uncut chip thickness? So what we are doing, we are trying to remove this much of thickness of material from the workpiece. So that is the T0 or uncut chip thickness. And this uncut chip thickness changes its thickness after cutting. So if you see the chip thickness after cutting, it has been increased. So it has increased because of the plastic deformation. So this is the cut chip thickness after deformation or after cutting. And another thing is what is shear plane angle. If you see this point, what you can see? You can see along this line, our we are the chipping action has been taking place, or deformation in the material is taking place along this line. So this line is called, or if you see along the width direction, this line will become a plane, and that plane is called shear plane, which is it is very important. And how much angle the shear plane makes with the cutting velocity, that is called shear plane angle, or it is denoted by phi. So these are the some terminologies which has been which is important in order to solve this problem. So now let's come to this problem. So what is given? So first thing, it is given orthogonal cutting, and the rake angle is denoted by which term? Here see, it is alpha. So this angle is given 15 degree. And uncut chip thickness, or T1, it is 0.3 mm. Similarly, cut chip thickness or deformed chip thickness, it is given by T2, it is given 0.65 mm. So there is a ratio which is defined by the chip thickness ratio. Chip ratio R, it is defined by T1 by T2, which is given 0.365, and if you solve it, you will get 0.46. And what is it? There is another term which is called shear angle or phi, shear plane angle. So we have been given phi or shear plane angle. This is the phi. So if you try to there is a relation between the R shear plane angle and this rake angle. So there is a relation. So that is explained in the video lectures of the course. You can go and you can watch it. So that relation is given by tan phi is equals to R cos alpha divided by 1 minus R sin alpha. So this is the geometrical relationship. So of course there are assumptions involved in deriving these relations. So that you can go and check in the video lectures. But the final relationship which we get between the shear plane angle and chip thickness ratio and the alpha or the shear plane angle. So this sorry, alpha is the rake angle. So between these three things, this is the relationship. And now we know all things, and what we have to do, we have to try to calculate by substituting the values. Then phi is given by tan inverse. Now I am substituting the values. Sorry, sine 15 degrees. And if you solve it, you will get phi is equals to 26.76 degrees. So this is the shear plane angle. And now what next thing has been asked, that is the strain. So there is also another relation with strain, shear plane angle and rake angle. So that is given by strain, we have been denoting by the word gamma or the letter gamma. So that is given by cot of shear plane angle or phi plus tan phi minus alpha, or strain is equals to, if we substitute the values, cot of phi already we have got 26.76 degree plus tan of 26.76 degrees minus what is alpha. Alpha is the rake angle, that is 15 degree. Now if you solve it, what you will get, you will get the values 2.88. So this is the value of strain, and this strain has happened because of plastic deformation of the workpiece material. So if you go and check what is the correct answer, so yes, so these are the correct answer. This is the correct answer, B. So it is approximately very close what we have got here. So the correct answer is the B. So is it clear to everyone, or still there is some doubt? If you have any doubt, please ask me. Okay, if it's clear, so we will move to the next problem. Please read the problem and try to find out means how to go for the solution. Please take some time to understand it, and then you can discuss with me how we are going to approach towards the solution of this problem. And if you have understood, then you can try to solve it by yourself, and you can give your response in the chat box. This problem is also a little bit extension of the earlier problem. Okay, before that, let's try to understand uh, some fundamentals of the chipping process or the forces involved during the cutting process. So uh, you keep on thinking, and meanwhile I will draw some diagrams. Okay, so here I have shown the tool and workpiece, and a workpiece is moving with a velocity v, and this is the rake face of the tool. And if you remember, what is this angle? This is nothing but rake angle or alpha. So this is tool, this is workpiece, and what is this? This is chip. Okay, and our workpiece is moving towards the right side with a velocity of the v. Same time, our chip is also moving with some velocity that we don't know, that is called vc. And because of these two relative motion, the chipping action has been taking place along this line. And if you remember, what what is it? It is the shear plane. So the deformation takes place along the shear plane, and the angle which it makes with the cutting velocity, this is the cutting velocity, v is the cutting velocity. So this angle is nothing but phi. So this is the phi. Now we will try to see what are the forces involved during the cutting processes. So if you see the rack surface, what is happening here? Our chip is moving towards this direction. So definitely there is a there will be a frictional force opposite to that. So that is the friction force that chip is applying on the tool, as well as chip is applying tool is applying on the chip. What another force which we can observe? Another force is that if you see this point here, the rake face of the tool is applying a normal force on the chip in this direction. So I am uh, so what I am doing, I am representing this same vector here. So this is the normal force and this one is the frictional force. And if we combine both, so that is the net force or R. So the resultant of normal force and friction force is represented by R. This is the total force which is tool is applying on the chip as well as the workpiece is applying on the tool. Now there is another set of forces which the chip is experiencing. Right now what we have denoted, this is the force which tool is experiencing because of the chip or the workpiece. Now we will try to see what are the forces which chip is experiencing because of the tool. So here our chip is getting sheared, or at this interface there is a shear motion is happening, or that is called V shear. And because of that shear, there is a frictional force is arising. Okay, so there is another friction force is arising on the chip. If you see the chip in 3D, it looks like something like this. So it has some cross sectional area. So chip looks like something like this. So there are two faces. So if you see that this surface, so this is the same surface here. So this on this surface here, tool is applying forces on. If you see the chip, so at this face here, on this face tool is applying force, whereas if you see the bottom face of the chip here, so here the force, it is also experiencing the force because of the shear deformation of the material. So chip is facing experiencing the force on these two faces. And right now what I am going to show the forces experienced by the chip on this shear plane, that is the shear plane. Face in contact with the rake face of the tool. Here it is chip. So now the forces I am showing here. So first one is the friction force, shear friction along this, and same time there is a normal forces also being applied on the chip from the workpiece. So here that is denoted by here. So chip on this face, chip is facing two forces. One is the along the friction force along the shear motion. Another one is the normal force perpendicular to the shear plane. So that is also, that is here. And if we take the resultant, so it is denoted by R dash. So chip is same, it is facing forces at the two different contact faces, but chip is moving at the constant velocity, that is Vc. So chip is not experiencing any kind of acceleration. What it means? It means net force on the chip is zero. Since chip is in the equilibrium, so net force on the chip will be zero. What is implies? It means these two resultant forces R dash and R, they must be equal. So they are equal in magnitude as well as opposite in direction. So now what I am doing, I am trying to plot these two force diagram at a same point. So again quickly I will show. This is the workpiece, this is the chip, and here we have tool. Okay, now just try to concentrate on the tool tip. So what I am going to draw the force diagram at the tool tip or the contact or the contact of the tool tip and workpiece. So, so parallel, I will use some different color. So there will be a friction force along the or parallel to the rake surface, and same time rake surface is applying a normal force to the chip. And what is the resultant? This is the resultant R. And now I will choose another color. Sorry. And our chip is facing another force, shear force here at this point. If you see, so it is also facing a shear force because of shear deformation along the shear plane. So it is somewhat this. So that is denoted by Fs. And there is another force that the chip is facing because of the workpiece in the perpendicular direction of the shear plane. So that is the normal force, or that is denoted by Fn. So if we take resultant of these two forces, that will also come along these two lines, and I have explained why they should be equal, because chip is in equilibrium, and that resultant is denoted by R dash. And if you see, so if you try to see the bigger picture of this, what is happening? Our tool is applying a force which is R on the workpiece, and same time our workpiece is applying a force R dash on the tool. So both are equal but opposite in direction. But this resultant force R, it can be resolved in any direction in in a plane. So if you remember, any force, if we have a force vector like F, we can resolve it any direction, like this or any two sets of direction which are perpendicular. So what else we are interested? We know what is the direction. This is the cutting direction. So this is V. And what is this direction? This is perpendicular to the cutting direction, or I should denote it by Z. If it is X, then it is Z. So we can also resolve this resultant force R along the X and Z, or along the cutting direction and direction perpendicular to the cutting direction. So this resultant force can also be resolved in another two directions. So it is like that. So this is denoted by this is denoted by this is called tangential force, or Ft, and the component of R which is along the cutting direction, that is denoted by Fc, or cutting force. So not now what we have seen, we have resultant force R, so we can resolve it in the cutting direction and tangent force direction. It can also be resolved along the F and N, and its same force can also resolve along the shear plane and direction perpendicular to the shear plane. And since they are the component of the same force, resultant force, therefore we can draw a circle with the diameter of R, and that circle will definitely pass through the all other points. Wait. So I will draw the circle in black. So this is the diameter, and all other points, they will lie on the same circle, and this circle is called merchant circle. So in merchant circle, this is applicable only for the orthogonal cutting. This merchant circle can be drawn only for the orthogonal cutting. So what merchant circle shows? It shows the relationship or geometrical representation of the different forces which is involved in the cutting process. So if you so there are different angles which I want to show here. So first thing is that, sorry. So first thing is that this angle. What is this angle? If you see, this is parallel. This force F is parallel to the rake face, and what we have shown, what we know from our earlier knowledge, that the angle between the rake face and this perpendicular which I have drawn is alpha, and this perpendicular direction is direction perpendicular to the cutting velocity. Since it is alpha, therefore this angle will also be alpha. This is alpha, and similarly, what is this angle? This is nothing. This is phi, or the shear plane angle. And there is another angle which is defined by tan of tan inverse of f by n. So we get another angle that is called lambda. So we have defined this angle, and this angle is denoted here. This is the lambda. Here if you see, this is the perpendicular, and if you take the tan, then you will get this angle. So these are the angles which are we are in these angles we are interested, and there are some relationships which our scientists have found out, like merchants and Lee and Schaeffer. They have derived some relationships based on these based on the energy minimization, or the power minimization during the cutting process. So they what they did, they derived the relation between, they tried to calculate the total power consumed with the help of material properties and geometric angles, whatever angles which we are showing here. And what they did, they tried to minimize the cutting power, and they and after minimizing they have got few geometrical relationship for given conditions, and those two relations are called mer- merchant theory and Lee Schaeffer theory. So now let's start looking at the problem. So by this background, I think we can go for the towards the solution of this problem. So what we have given, we have been given a rake angle or alpha. Alpha it is given, that is 15 degree, and T1 is the uncut chip thickness, that is 0.3 mm. T2 is the chip thickness after deformation, that is 0.65 mm. It is same as the earlier, and with the help of T1 and T2, if we try to calculate R is equal to T1 by T2, that we can get 0.3 divided by 0.65, 0.46. It is same as earlier. And again, if we try to calculate the shear plane angle, that can be calculated by this relationship, sorry, or sine alpha. And if we use this relationship and we substitute the values, we will get y is equal to 26.76. So let's talk about the first theory. So you can go and you can see the derivation of this relationship, how this relation has been arrived, that has been explained in the lecture. So I am directly writing the final outcome of the theory. So first theory is Ernst and merchant theory. So we have got 2 phi plus lambda minus alpha is equals to pi by 2. So for the minimum power consumption, this relation holds true. So in this relationship, what we have and what is unknown. So we have phi, we have alpha, only unknown is lambda. Lambda is nothing, it is the friction angle. And it is defined by lambda is equal to tan inverse f by n. So if it substitute the value of uh, phi and alpha, what we'll get? We'll get 2 into that is equals to pi by 2. If I will write in degree, that will comes 90 degrees. So lambda will come 51.48 degree. So by the merchant theory, if we try to find out what is the lambda for the given geometry, for the given conditions, what was the given condition? We were given that the rake angle is 15 degrees. So that is what it is representing. If rake angle is 15, that means the tool geometry is fixed. And for given uncut chip thickness, that is T1, that is given by that is given 0.3 mm. And finally what we are getting 0.65 mm of chip thickness. For these conditions, what was the friction angle? That we can calculate by this Ernst and Merchant theory. Similarly, if we try to see what was the another relationship, that was Lee and Schaeffer theory. He also did the optimization, and what he got, this relationship. So now what we can do, we can substitute the remaining values, and we can try to find out what is the value of lambda. So we will put 45 degree. So finally we will get lambda is equal to 33.24 degrees. So we can see if we use different theories, we are getting significant difference in the results, and that's where the uh, properties of the material comes into the picture. So any of these theory is not universal. So they have been made for special conditions and special types of material. So for ductile material, we have different theory. For brittle material, we have different theory. For uh, plastics, that is different. For metals, that is different. So people have done, and they have tried to find out some relationship that is applicable to very limited domains. So before applying any theory, we should know which theory is applicable where. So but if we talk about the answer of this question, so for the Ernst and Merchant theory, the friction angle is 51.48, and for Lee and Schaeffer theory, 33 point friction angle is 33.24. So which is the closest one? C. Yes, so correct option is C. So any of you have any doubt in the solution of this problem? Whether all of you have understood the procedure or not? You can give your response in the chat box. Do you need any clarification in any step? Okay. Okay, so it seems everyone have understood this problem. So let's move to the next problem. Please read the problem and you can give your response in the chat box. It is directly from the lecture, so you won't find much difficulty. Okay, I think most of all of you have got the correct answer. So, still, I will quickly let you know what others are. So, uh, which of the following is the correct relationship between the rate angle alpha and shear angle phi and friction angle lambda as per the Stabler's relationship? So, the first one, it is nothing. It is Lee and Schaefer. And if you see the second one, these two relationships we have used in the previous problems, you can remember. So this is nothing but Ernst and Merchant theory. And this is this relationship we haven't seen, but if at the place of pi by 4, if there would be some constant cm, so okay, what I will do, I will write it again. Suppose if it was not pi by 4, if it was, it is very similar to what is called merchant second theory. Merchant second theory, or so there, what is there, how it is defined, 2 phi plus lambda minus alpha is equals to some constant cm. So basically this cm depends on a constant k value. So these values are defined, they are means given by the scientist called Prisman, and it is nothing but a multiple of which the normal stress in shear plane would formulate a part of the ultimate strength and shear of the material. Yes, so basically, any force, when we apply any force, that is uh, uh, all all the force component is not responsible for the deformation. So only some part of is responsible for the deformation, and that is working along the component which is working along the shear plane, that is responsible for the deformation. So that comes into the picture, means, so if that was the case, then it was the merchant second theory, and the last one is the correct answer, and that is called a Stabler's relation. So the correct answer is the last, and it is just a memory based problem. So we will move to the next problem. Please read it. It is also easy one. So I hope all of you will give the correct answer for this. Yes, all of you are correct. So what is the question? So it is the which of the following process is not grouped under the metal removal process? So as the name suggests, metal removal process, the process should involve removal of some material, removal of material. So that is, so or this is the synonym of the machining process. So, and all of you know that the machining process, our aim is to get the final uh, sh- shape and size, or we should get the accurate dimensions of the machine, or we are aiming for the uh, good surface finish. And for that, what we are doing, we try to remove some portion of the material from the workpiece, and we make it as accurate so that it should be useful for and so that it should fulfill our functional requirements. So boring, if you remember, what was the boring? So you can see in the diagram, boring is the process which is used to increase the diameter of the some hole. So you can see, uh, earlier we had hole of this size here, but with the boring tool, so boring tool something look like this. With the help of boring tool, it keeps on rotating and it removes the extra material. So it removes the extra material here and it increases the diameter of the hole. So it is here. So again, it removed some material in order to increase the diameter. So that is the metal removal process or machining process. Next one is milling. What is milling? In milling, we are trying to create some surface. So either it may be flat one or it may be curved one. So based on the different situations, there are lots of uh, types of the milling operations. So face milling, end milling, profile milling, pocket milling, surface contouring. So these are the few examples. But the final aim is to remove submaterial in order to get the required geometry or the required surface geometry. So in the milling operation, we are creating some surface, or it may be flat, it may be curved, or it may be having some 3D contours. Any complex geometry we can make by milling. So here also material removal is involved. Now let's come to the extrusion. Extrusion is a little different. Here extrusion is the primary process where we deform the material. We are not going to remove any material, where we are just deforming the shape of the material, or we are changing the shape of material by applying temperature or by applying force along with temperature. So here only shape change is involved. Shape change. So extrusion is nothing. Extrusion is the process to get a component which has uniform cross sections like tubes, bar, or eye section. So the process is very easy. We have some die, and inside die we are putting some billet. It is shown already in the red. So this is the billet, and we are trying to push the material or the billet with required cross sectional geometry. So what we do, we apply some force on the billet. Sometimes we increase the temperature also so that process become easier. And finally, what we are getting a component with uniform cross section, or the tubes, bars, something like that. But here only shape change is involved, no material removal. Final one is drilling. So in drilling, it is very common. It is used for creating holes. So here we have a rotating tool. So this is the tool, and it is rotating, and same time it is given downward motion through the workpiece, and because of the downward motion and circular motion, it is creating a final cylindrical shape or hole. And the material which is removed, it comes out through the helical path which is given in the along the periphery of the drill bit or the drilling tool. So material comes out in the form of conical helical chip. So here also material removal is involved. Therefore, it is the machining process or material removal process. So correct option is extrusion. Now we will move to the last question of the day. Please read it and try to solve it by yourself first. After that, we will discuss it together. If you are finding any difficulty to understand the problem, you can ask me. Okay, so let's try to understand the problem and what is being asked and how to approach it. So, first thing, what has been asked, what will be the coefficient of friction in machining, and what are the values we are given? Ft. What is Ft? Ft is the tangential force. And what is Fc? It is the cutting force. And what is alpha? It is the rake angle. So we have been given the cutting force, tangential force, and alpha, and we are looking for coefficient of friction. And if you can remember how coefficient of friction is defined, that is defined by frictional force applied by rake surface on the chip divided by normal force applied by rake surface on the chip, that is defined in, that is equals to the mu. So we don't have F or N, we have been given FT and FC. So we have to find out some relationship between F and N with the FT and FC. So again we will draw the same geometry. So we will have workpiece. So there is a chip, and same time we have a tool, and what is this angle? This is nothing, again it's alpha, and I will draw some different colors. So again we will draw the forces on the which the chip is experiencing. So along the rake face it will experience a friction force, and perpendicular to the friction force, what it will experience? It will experience a normal component of this force, and this is the resultant. Similarly, if you see along the shear plane, this is the shear plane. Okay, so along the shear plane there is another force which the chip is experiencing, so that is towards the opposite direction of the, see, our chipping action is happening, taking place in this direction. So there is shear velocity, so the friction will come in opposite, and same time a perpendicular force which is acting on the chip on the shear plane, that is Fn. So these two are Fn, and now we have to show what is the cutting force and tangential force. So we know our workpiece is, sorry, our workpiece is moving with velocity v towards the left, so the cutting force will also experience in the same direction. So something like this. So that is the FC, and perpendicular to the FC we are having tangential force, that is FT. Here we have 90 degree, here we have 90 degree, here we have 90 degree. Since this angle is alpha, therefore this angle also be alpha. Okay, and if this is alpha, so between what forces we are looking the relationship, that is with F and N to FC and FT. So we are interested in the angles between F, FC and FTs. So I will just show the one of them. Then you can using the geometry you can also find all other relationships. So it is alpha, and if you see what is this angle total, it is 90. So if you try to find out what is this is nothing, this is 90 minus alpha. Okay, so if we try to write the what is the this friction force between the chip and the tool in the terms of FC and FT, so what we will get, F is equals to FC cos 90 minus alpha. Okay, so FC is here. If we take the component of FC along the F, or something like this. Okay, so this length we will get. Okay, so if we take the projection of cutting force on the friction force, we will get this equation, and this is the value. But friction force is also means there is, if a component of tangential force will also contribute to the friction. So if we draw a line parallel to the F here, okay, so I have drawn a line, this line, which is parallel to this uh, blue one, blue F. So if we try to find out the angle between them, this is again nothing but alpha. So how much this distance will be? It's nothing. It will be Ft cos alpha. So what we can write, F is equals to Fc cos 90 minus alpha is sin alpha plus Ft cos alpha. And already we know what is the alpha. Alpha is 15 degrees. Now we will substitute. What we will get, F is equals to, what is the Fc? Fc is 1200 newtons. Fc sin alpha sin 15 degree plus Ft. Ft is 400 newton cos 15 degree. If you calculate it, you will find out F is equals to 696.95 newtons. So friction force, which is chip is experienced from the rake phase. So this friction force is 696.95 Newton. And similarly, if you try to find out the relationship between the normal, this force, and Ft and Fc, you will get Fc cos alpha minus Ft sin alpha. And again, if you substitute the values, n is equals to nothing, 1200 cos 15 degree minus 400 sin 15 degrees, or n is equals to 1055.58 Newton. Now we have got the F, we have got the N. We will take their ratio in order to find out the coefficient of friction. So mu is equal to 696.95 divided by 1055 58, which will come to 0.66. So the correct answer is A. So I have explained the solution of this question. Still, if any of you have any doubt, you can ask me. Is it clear to everyone? Okay, any of you have any doubts? Okay, if there is no doubt, then probably we can start our session here and we can meet next Tuesday with some problem based on the video lectures of the course of the week 6. Okay, so if you have any doubt, please feel free. Okay, okay, so wish you all the best. So good night to all of you. Thank you.